All right, we have momentum. Of course, we have two kinds of collisions. We have elastic and inelastic collisions. Okay, so let's say I've got a car or a truck that's moving and it's going to collide with a car. Let's do an inelastic collision first. So let's call this one M and this guy little m. Okay, so this guy's not moving at all initially, so I'm going to go M, okay, multiplied by the 10 meters per second plus a little m times 0 equals, okay, here we go. It's going to then be big M plus little m. Okay, and we're going to multiply that by some common v final, like that. Okay, and then we can figure out what the velocity final is. The impulse, which really is the letter J, does equal the mass of one of them multiplied by its final velocity minus its initial velocity. Now you can do that for either one of these. It doesn't. You have to do them separately. So if I'm going to do it for the big truck, I'm going to say big M, which looks like 3,000, times whatever our V final is here minus the 10, and that'll be the impulse. Now I can do it also for the small car. So I'm going to take its mass times its change in velocity. So it'd be 0 initially, and then V final is whatever the V final is there. We have to remember though that impulse, okay, capital M, or M V2 minus V1, okay, is also equal to force times time. Okay, so force times time. So impulse is always force times time. Okay, so remember that as time goes down, the force of the collision gets bigger. Remember, that's equal and opposite. Okay, the force applied from the collision to this big car or big truck also equals the force applied, okay, to the small car, but equal in opposite directions. Now, while we're talking about impulse, let's remember force times time graphs. Okay, if I look at a graph like this, the area under that curve is equal to the impulse. Now, while we're talking about, I just remember something else I can talk about. If we do a force distance graph, okay, the area under that graph equals work. And remember that work, as long as there's no non-conservative work, goes to change in kinetic energy. So these are two common graphs that we have that we take the area under to get a quick result. Okay, now what if we're doing an elastic collision? This side of the equation will stay the same, but the ending is going to be equals M1, I'll call it M1, and then V1 final, that's the big capital M, plus little m, call that little 2, I guess, V2 final. Okay, and you can call these objects whatever you want to, but notice what happens is this side stays the same, but now I've got two objects moving separately afterwards, after the collision. But I can use a kinetic energy equation to get this equation solved for. So in a nutshell is what momentum is about. Okay, so just remember our shortcut. You know, force of a collision does equal change in momentum over change in time. That's something we've talked about in class a couple times. And remember, P is our formula. P is momentum equals m times v. Okay, now there is a ballistic pendulum for us to look at. So what if a bullet is shot at a ballistic pendulum and it swings up to a new height maximum? Remember, the height of a pendulum does equal L minus L cosine theta. So we can find a height of a pendulum. Sometimes they tell you what the height is. Okay, so we actually have to look at the right half of this. The bullet hits, it swings up to a new maximum height. So we need to figure out the velocity of the bullet, but we need to know what the velocity of the bullet and the mass, once they collide together, how fast is it going? Well, once it hits, these two have kinetic energy, and it swings up to gravitational potential. So that's what first part we're going to do. We're going to do kinetic energy, and that goes to gravitational potential energy. Okay, so then what am I going to do? I'm going to say 1/2, and I'm just going to say m because I know they're going to cross off. 1/2 v squared equals mgh. I'll know how high the pendulum goes. My masses cross off, so I don't need to worry about that. I can get my velocity. Now that velocity is the velocity just after these two collide. So I can figure out the mass or velocity of my bullet by doing this. So inelastic collision, m times v naught, okay, plus big M times 0 equals, okay, little m plus big M, okay, times v. And this v is the one you just got there. It goes in there. Then you go back and you can solve v naught for the mass of the bullet. Now let's talk about, again, the differences between these two. This is an inelastic collision, and we know kinetic energy is not conserved. That's by definition what an inelastic collision is. An elastic collision is one where kinetic energy is conserved. So in this second case, when I have an elastic collision and this right side of the equation has two objects moving afterwards, I will have two unknown variables. But I can do a systems of equations, probably not going to be on the AP test, but you can do that, where I go 1/2 the big mass times its beginning velocity squared. I'll say v1 naught squared. I don't know how to label this. Plus 1/2 little m times v2, I'll say naught squared, equals 1/2, again, big one, big mass, I've been calling that mass 1, times v1 final squared, plus 1/2 little m times v2 final squared. Okay, so I can summarize the kinetic energy before the collision equal after the collision. Now I have a systems of two equations that I can use to solve for the final velocity. Okay, and we can look at angular momentum when we talk about rotational. Okay, but the same rules are really going to apply for angular momentum, that momentum is always conserved before something happens and after something happens, assuming that there's no outside force involved. So momentum is always conserved if there's no outside force involved.